Hello everyone and welcome back to Skitame Learning. Today we are going underground. Millions of people around the world walk into a subway station, wait for a train, ride a few stops, transfer to another line, and walk out. It feels simple, but behind that trip is an enormous mathematical machine. Today we are going to explore the hidden mathematics of subway systems. And because we are here in the Washington, D.C. metro region, we'll use the Washington Metro to help us uncover some of that mathematics. So grab your imaginary smart trip card. Let's ride. Distance is not the same as number of stops. Let's suppose you are traveling 5 stops. Does that tell you how far you traveled? Let's look at this rough sketch of a subway system. So we'll call this the red line, okay, and this is the green line. Okay, so the red line has 4 stops: A, B, C, D, and then the green line has three stops, so C, E, F. Okay, and let's assign numbers or distances to these stops. Okay, so we go to this page here. Again, this is the red line. This is the green line. Okay, so from A to B, 0.5 miles. From B to C, 0.8 miles. From C to D, 1.2 miles. And then we go to the green line. From C to E, 0.6 miles. From E to F, 1 mile. Okay, so that is recapped here. So A to B, 0.5, B to C, 0.8, C to D, 1.2, C to E, 0.6, and then E to F, 1 miles. If we add all this, we'll come to 4.1 mile. Okay. 5 stops produce a journey of about 4.1 mile. But another 5-stop journey could be shorter or much longer. That's why subway mathematics depends not only on the number of stations, but also on the distance between them. Okay. As we all recall, distance is equal to speed multiplied by time. Okay. Now let's for a minute suppose that a train travels 6 miles at an average speed of 30 miles per hour. How long would that train take if we ignore the stops? Okay. So it's going to be 6 divided by 30. That's roughly 0.2 hours. Okay. Now convert that to minutes. So it's going to be 0.2 multiplied by 60. So that gives us 12 minutes. But subway trains stop. Doors open, passengers leave, passengers enter, doors close. The train accelerates again. So actual travel time will be longer than our simple 12 minutes calculation. And that's where subway scheduling becomes much more interesting. Let's explore the mathematics of stoppings. Let's say our train makes 8 intermediate stops. Suppose each stop adds an average of 30 seconds of station time. Okay, so we are looking at 8 times 30 seconds. That gives us 240 seconds. Okay, so 240 divided by 60, that gives us 4 minutes. Our original 12 minutes theoretical journey becomes at least 12 plus 4. So that's 16 minutes. And we haven't even included slow acceleration, braking, signals, congestions, or delays. One little number, 30 seconds, repeated several times, can significantly change an entire journey. That's multiplication at work. How often should trains arrive? Now, we reach one of my favorite subway calculations: frequency. Suppose trains arrive every 6 minutes. So 60 divided by 6, that's 10. That means approximately 10 trains per hour in one direction. Okay. What if trains arrive every 4 minutes? So that's going to be 60 divided by 4. So that's 15. Okay. That means you have 15 trains per hour going into one direction. Now let's compare 6 minutes interval to 4 minutes interval. So 6 minutes gives us 10 trains per hour. 4 minutes gives us 15 trains per hour. That's 5 additional trains per hour. The time, be- the time between trains is called the headway. Okay. And notice something interesting. A difference in only 2 minutes in headway can dramatically change how many trains the system can move. Okay. Next, let's explore passenger capacity. The number of passengers a subway system can move doesn't depend only on how often trains arrive. It also depends on how long the trains are. A subway system may operate trains with different numbers of cars. For a simple example, let's compare a 6-car train with an 8-car train. Okay? Let's assume that just for our mathematical example, that each car can carry 100 passengers. Okay? So 6 cars with 100 passengers, looking about 600 passengers per train. Now let's make the train longer. Okay, 8 cars multiplied by 100, that gives us 800 passengers per train. So that additional 200 passengers, that's roughly an increase of 33% more capacity from 6 cars to 8 cars. Okay, and now what happens when we combine train length with frequency? Suppose trains arrive every 6 minutes. Okay, so 60 divided by 6, it's about 10 trains, right, per hour. With 6 cars, okay, you're looking at about 10 times 600, which is 6,000 passengers per hour. Okay, with 8 cars, we have 10 times 800. That gives us 8,000 passengers every hour. Same hour, same 6-minute headway. But simply changing from 6 cars to 8 cars gives our simplified example room for 2,000 passengers. That's an addition for each hour. And subway planners can work with both variables. So 6 cars, 600 passengers. 8 cars, 800 passengers. So this is for the train length. Okay. For the frequency, so we have every 6 minutes, we have 10 trains per hour. And for every 4 minutes, we have 15 trains per hour. So passenger capacity isn't controlled by just one number. You can change how many cars are on the train or how frequently the trains arrive, or sometimes both. That's the hidden mathematics of subway capacity. So now let's examine the mathematics of transfers. Okay. Coming back to our previous example, so we have A, B, C, D, each letter representing a train station. Okay. And another line crossing C here, we have E, F, okay, G, and H. Okay. You cannot stay on one line. You must transfer through C to go toward this direction. So you have this direction and you have that direction. But to go from this line here, you have to go down that line, but transferring at C. Okay. So travel time on line 1, which is, let's say, or the red line. Okay. Wait time. So you have transfer time, waiting time. Okay, and then you have, this is for the red line. And then you have travel time on the green line. Okay. So suppose the red line gives you 8 minutes of ride. Transfer, walk, 3 minutes. Waiting, 5 minutes. Okay. This is for the red line. For the green line, 9 minutes. Okay. So we are looking at 8 plus 3 plus 5 plus 9. So that gives us a total of 25 minutes. But suppose another route takes 12 minutes on the first train and 10 minutes on the second train, but requires almost no waiting. That route could actually be faster. So the route with the shortest distance isn't necessarily the route with the shortest time. That's optimization. Why subway maps don't always look like a real geography? Here is something fun. Look carefully at many subway maps. The lines often appear beautifully straight. Stations are evenly spaced, intersections look neat, but real subway tunnels aren't necessarily arranged that way. Why? Because a subway map has another mathematical job. It must communicate information efficiently. Okay? So you have curves like this. Okay? This is actually the way a subway network is on the ground. But they will never show this on the map. Okay? So this is going to represent the real stuff in real life. Okay? So coming back to that, so we have A, B, C, D. Okay? This drawing may represent geography. Now, coming back to this drawing here, this one here may represent the actual network. For a passenger, the most important questions are often where I am, which line do I need, where do I transfer, how many stops. Where do I get off? A subway map, therefore, sacrifices some geographic accuracy in exchange for clarity. That's mathematics meeting design. So let's look at a simplified visual of the metro DC metro system, WMATA. The green line, which is like this, and the blue line, which is like this, roughly. Okay. So a passenger doesn't need to understand graph theory to ride the metro, but graph theories is hidden underneath the trip. Every time you ask, where do I transfer? Which route? Which route is faster? How many stops? How long will I wait? You are asking a mathematical question, and your phone or trip planner is essentially solving an optimization problem for you. So let's finish with today's DMV math challenge. Suppose you are riding metro. You have two possible routes. Train ride, 18 minutes. Transfer, 4 minutes. Average wait for connecting trains. Okay, wait, 6 minutes. So the final ride is 12 minutes. Okay. On route B, train ride, 24 minutes. Transfer, 2 minutes. Average wait, 2 minutes. Final ride, 10 minutes. Which route is faster based on what you're looking and by how much? Please pause the video, calculate it, then put your answers in the comments. And here is the bigger question. Would you choose the mathematically faster route or the route with fewer transfers? Because mathematics can tell us what is fastest, but human beings still decide what is most convenient. The next time you are riding on a metro platform watching the arrival countdown, remember, you are surrounded by mathematics. So you have time, distance, speed, frequency, capacity, probability, okay, network, optimization, geometry, all before the train even arrives. So the next time you step onto a subway train, don't just see tracks and stations. See a mathematical network moving thousands of people from point to point. If you enjoyed today's journey, please like the video, subscribe to Skitami Learning, share it with someone, and tell me in the comments what mathematics you noticed the next time you ride the metro. Until next time, remember, mathematics is everywhere. Sometimes it's right underneath your feet.